Hello, and welcome to lesson 24 of this Introduction to Probability of Wolfram. The topic for this lesson is the normal approximation to the binomial. Let's begin. In lesson 18, you saw that the binomial distribution could be approximated using the normal distribution. This approximation is good if the variance is greater than or equal to 10. But the approximation gets more and more accurate as n grows and tends to infinity. In this lesson, you'll learn more about this approximation. So what's the claim? The theorem of normal approximation to the binomial can be stated as let the random variables b stand for the binomial distribution np and z for the standard normal distribution. Then the probability b minus the mean divided by the standard deviation, in other words, b standardized, is between a and b, tends to the probability z is between a and b as n goes to infinity. In the same way that n is large in the law of large numbers, if n is large, the claim is that the binomial is replaceable by the normal distribution. Equivalently, in terms of the PDF, this would mean that the PDF of the binomial distribution tends to the normal distribution PDF, where the mean and the variance of the normal are the same as the binomial distribution. So, before the proof, you'll need an approximation that comes up very often when transforming something from discrete to continuous. It can be stated as the factorial of n is approximately the root of 2 pi n times e power minus n times n power n. This approximation is derived from this equivalence, which accomplishes the same thing, although the right-hand side is harder to compute. This approximation was named after James Stirling, a Scottish mathematician who perfected the formula, but the formula was first stated by Abraham de Moivre. From the visualization, you can see this approximation is clearly good, especially for large values of n. Now, the proof of the normal approximation to the binomial. Assume n is a large positive number. Let's start with the binomial PDF, with the binomial coefficient, which can be fully expressed using factorials. Then, using the Stirling approximation, you get this. Now, with a bit of isolation, you can simplify the expression to this. These approximations are proven through multiple log identities and inequalities, and are written with these variables for the convenience of this proof. So replace these approximations with the first one, and then the second one. And you have the PDF of the normal distribution. So when n is large, the binomial distribution is approximatively the same as the normal distribution. Practically, how can you apply this approximation? Assuming your binomial distribution is well defined, how can you approximate it? Well, the first step would be, of course, to set the mean to NP and the standard deviation to the root of the binomial variance. Now, for the probability, you'll need to adjust the bounds. Here are the two distributions overlaid. Let's consider this probability. If you don't adjust the bounds, it may look like this, where orange is for the binomial and blue is for the normal distribution. Let's say our bounds are inclusive. Then the lower bound is inclusive, so decrease the lower bound by 0.5, and the upper bound is included, so increase the upper bound by 0.5. On the contrary, if the binomial probability bounds are exclusive, then increase the lower bound by 0.5 and decrease the upper bound by 0.5. Let's try an example. You roll a die 180 times. What's the probability you roll a 1 at least 20 times and fewer than 30 times? Notice 20 is included and 30 is excluded. You can find the probability of the binomial directly from the distribution and n probability. Now, what about the normal approximation? Before any approximation, always confirm the approximation is valid. Here, check the variance is greater than 10. Then for the probability, the lower bound is inclusive, so 20 minus zero point 0.5, and the upper bound is exclusive, so 30 minus 0.5. But what's the significance of all this? What are the implications of this theorem? Well, an interesting property of binomial distributions is that the sum of two binomial distributions is also a binomial distribution. In other words, increasing n in the binomial distribution is equivalent to adding binomials together. Or inversely, each binomial is n divisible. That changes the perspective a lot. The theorem of normal approximation to the binomial can now be reformulated as a sequence of n identical binomial random variables, whose sum tends to the normal distribution as n tends to infinity. In a sense, this is the weak law of large numbers, only applied to the binomial, and leading to an approximation of the normal distribution. So, in summary, factorials can be approximated using Stirling's formula, which is useful for transferring from discrete to continuous contexts. The normal distribution can approximate the binomial distribution with a large n. It can also be expressed as this statement. A large sum of identical binomial variables can be approximated as a normal variable. It turns out this is only the beginning, though. Like the law of large numbers had a weak and a strong version, this approximation can be extended in a much stronger way, which is the subject of the next lesson, arguably the most powerful theorem of all probability theory, the central limit theorem.